Good evening and welcome to our kickoff event for celebrating National Astronomy Week 2020 Mars Encounter. We are so excited to be here with you and thank you for joining us. As you may have noticed in the intro video, the NAW is composed of several astronomy organizations around the UK. You can find out more about us at astronomyweek.org.uk. Hello, my name is Lucinda Offer and I'm delighted to be the chair of National Astronomy Week Mars Encounter. Tonight we have two other hosts with us. Please introduce yourselves. I will be a host, as well as we have Joe Fox and Robin Scagel. Would you guys both please say hello?
Hi,
Hello.
I'm Joe.
Okay, excellent, thank you. So it is also our kickoff event of 9 days of NAW from the 14th to the 22nd of November. You can register for our other events at Eventbrite if you just search for NAW 2020 when you go to the website, or you can go to our website at astronomyweek.org.uk. where you might find local online events to celebrate this week. You'll find others that are going on around the UK other than our own. So maybe you'll find something local to you. Before we get started, though, I am going to pass on to Robin to give us a brief history of NAW and acknowledge its founder. Robin, go ahead.
Okay, that should be right now. Okay, what I'm going to talk about is very briefly the background to National Astronomy Week and the story of National Astronomy Week. Don't worry, it's not going to take very long. It all goes back to 13th of March 1781, a rather long time, 200 years ago. Over 200 years ago, William Herschel discovered the planet Uranus from Bath, and this was a major discovery in astronomy because it was the first time a new planet had actually been discovered by anybody. And of course, because it was discovered from the UK, we all thought that it would be a good idea to celebrate it. And so it was suggested that a National Astronomy Week be held. Incidentally, the telescope, the big telescope there, you see him, this is a rather fanciful 19th century illustration. This is the actual telescope that he used to discover the planet Uranus, quite a small one from his back garden in Bath. And it was the idea of someone called Robin Gorman. In fact, it was suggested by a few people, including Storm Dunlop, but Robin Gorman was the one who took the idea and ran with it and got a lot of people together and discussed this around a table and said, why don't we do something for National Astronomy Week, have an Astronomy Week to celebrate the discovery and get people all over the UK looking at the sky. And so that was what was done. And this is another big telescope, a much bigger than ones I've shown you so far. The reason I'm showing this is because because of the importance of William Herschel to astronomy. During National Astronomy Week in 1981, there was a big event held at Greenwich, and this instrument, the name of this instrument was revealed, and it still is the William Herschel telescope. So that was a big kickoff for National Astronomy Weeks, and we've just carried on since then. Here's a list of the ones we've done. A few years later, 1985, Halley's Comet was visible. It was a bit of a washout in the UK, but nevertheless, and it didn't look anything like that from the UK, but in November 85, we all got out and looked up at the sky and held a National Astronomy Week, a big event. And incidentally, at that time, because it was such a big thing, we got a huge amount of money to celebrate the event. We had £25,000 from the Daily Telegraph, which was organised by a guy called Brian Harper. And we actually had a concert at the Wembley Arena to celebrate Halley's Comet. It was a big event. But the comet itself let us down a bit because it wasn't all that spectacular. Here are the other ones that we've had. 1990, we had the one to celebrate the centenary of the British Astronomical Association. In 1996, the 150th anniversary of the discovery of Neptune, which wasn't done from this country, but there was a British connection, which I won't go into now. It's quite an interesting but an amusing story, but it's another matter. Then in 2003, we had another really good year, the closest approach of Mars for nearly 60,000 years, and it was really large in our telescopes, and that was held in August, lovely warm night, and the media all covered it in great detail, and we had thousands of people turning up all over the country to look through telescopes at Mars. Then in 2009, we thought we'd have another week, and this was usurped a bit because the International Astronomical Union decided also to do an event. And so we limited this just to one day, because this was the 400th anniversary of the first use of the telescope, which everyone thinks was Galileo. But as we know in Britain, it was actually the first use was by Thomas Harriot from Science House in Middlesex. And he made a lovely drawing of the moon through his telescope. So we were very concerned that very enthusiastic about pointing out that it was actually the first British use of an astronomical telescope on the sky and not Galileo. And then in 2014, we concentrated on Jupiter, which was then very high in the sky. At all of these events, the key thing has been to observe the sky. And normally, this is what we do. As astronomical societies around the country have observing events, and thousands of people literally turn up all over the country to look at the planet through the sky, or objects in the sky. But this year that hasn't been possible. So that's why we've gone for an online event only. Just to finish up with, this is the steering group, or some of them, that have been bringing a National Astronomy Week to you, and you can find their pictures online. And so that's the background to National Astronomy Week, and it was all the vision of one man, Robin Gorman, who sadly died a couple of months ago. So this is a tribute to him. And now I'll hand back to Lucinda.
I just want to say thank you so much, Robin, for that. Before we get started, first I want to remind you that we will be taking questions, and you can use the Q&A icon on Zoom, or if you're joining us on YouTube, in the chat box. And this evening's theme is Mars the Planet, and I would like to introduce to you Chris Lintott, who is a professor of astrophysics at the University of Oxford, and best known as the co-presenter of the BBC's long-running Sky at Night program. He's going to tell us all about it, along with our two other very special guests tonight, Professor John Bridges and Jane Greaves. Chris, on to you.
Thank you very much. It's a delight to be here and to kick off this very special and unusual National Astronomy Week. I'm just going to talk for a few minutes to give some context of why we're talking about Mars and why it is that we're excited about Mars in this moment in particular. And then my colleagues will talk about the red planet and about life in the universe. I think if you want to understand why Mars has a particular fascination, and has done throughout human history, if it's clear where you are after we finish this event, you should go outside and look up in the southeastern or southern sky, and you'll see a bright red star, which is the planet Mars, easily on view in the evening sky right now. Mars, when it's brilliant and bright in the sky, looks like nothing else. It can outshine almost everything else, and it has this distinctive red color, which distinguishes it from almost anything else you'll see with the naked eye. And for as long as people have been looking at the sky, people have been speculating about what this planet might be like. It is our nearest neighbor, the fourth planet out from the sun, one out from us. And people have always assumed, or assumed for many years, both that it's a place that we could visit and that it's a place where life may exist. And if you're a fan of H.G. Wells, that maybe life might come and visit us. So people have always dreamt of going and walking on the red planet's surface. This is the latest in an extremely long line of visualizations. This is a recent NASA concept of what the first humans on Mars might look like as they begin their exploration. And I think this sort of image gets across, if nothing else, the idea that it's a world, a place that could be explored. You can imagine standing on Mars. You can imagine weather on Mars. You can imagine setting off over the desert landscape there. But as I said, it's also almost always been a place where people have imagined there being life. And the story of the history of the exploration of Mars, particularly once telescopes began to point towards the red planet, was one of increasingly sophisticated speculation about life, which reached its peak in the 19th century with these famous observations. These are drawings of Mars. Think of it as a map of the planet, drawn by an Italian observer called Schiaparelli in the late 19th century, 1886. And you can see here there are some dark regions on the planet, but Schiaparelli, who had access to some of the best and most advanced telescopes of his time, saw on the surface of Mars a network of channels, canali in Italian, which, as you could see, he drew it as often double places, double features. And these canali were translated into English as canals, and many observers thought that they were observing a canal network produced by intelligent observers, channeling water from the polar caps down to the desert regions to irrigate what must be a planet-wide irrigation system. At this point, you could imagine learning from the Martians and visiting them. One of my favorite stories is that of a prize established in the early 20th century by the French Academy of Sciences to the first person to establish contact with alien civilizations, but Mars was excluded. You didn't win any money if you contacted Martians because that's too easy. Now, it turns out the canals don't exist. Here's a later map. This is from Antoniadi, an observer in 1929 using a big telescope in Paris. And Mars today is devoid of both canals, vegetation, and alien life. This is the best ever image of Mars taken from Earth, or at least near Earth. This is the Hubble Space Telescope view from a few years back. And in this image, a pixel is about 20 to 30 miles across. So let me give you a brief tour of what we're looking at here. Most of the Martian surface is a dusty desert, though some areas are blown clean of dust. Those are the darker regions. And these markings change and alter under the influence of what can be quite severe dust storms. If you've seen the movie The Martian, you know that Mars can be subject to global dust storms. There are polar caps made of water ice, but also carbon monoxide and carbon dioxide ice. You can see there's a small polar cap up at the top there. This image is taken in Martian spring in the northern hemisphere. And the white wispy things you can see, particularly on the right there over a feature called Syrtis Major, those are clouds in the very thin Martian atmosphere. So Mars does have weather, though nothing so exciting as rain. So this is an Earth-like but very different place from our own planet. It's a place where temperatures can be extreme. One of NASA's Mars rovers measured a peak temperature of a rather balmy 35 degrees centigrade, but typical nighttime temperatures drop to minus 150 degrees. So this is a cold place. It's a dry world, it's a desert world, though we have good evidence, as we'll hear from one of my colleagues in a second, that Mars was once a wet world with a thick atmosphere. In the early days of the solar system, it will have looked much more like an Earth-like environment, something that changed as it lost its thick atmosphere. And much of the study of Mars today is an attempt to understand what past Mars was like, and how it got to be that way, why this planet ended up so different from our own. There are still reservoirs of water ice underneath the surface. We know there's at least one and probably several brackish lakes hidden under the polar caps. And people speculate that it's possible that simple life, bacterial life, may still exist on Mars today. And several of the missions that are on their way there now, or which are being developed, are aimed at exploring that possibility. That's why I'm delighted that we've got Jane Greaves, an astrobiologist, on the line as well. And she'll be talking to us about life in the universe after we've heard a little bit about Mars. So these are the outstanding questions for Mars. Why is it different? Was there ever life? Is there life there today? and how has it changed over the 4.5 billion years of cosmic history that it's shared with the Earth. And that's the final point I want to make, really, is that we have thought since the early days of Mars as a place we can visit, as a place we can explore, as a place that might host life. But it's also a place we can go to get perspective on our own position in the universe. This is my favorite photo sent back by a Mars mission. It's a picture from the Mars rover Curiosity, robot geologist that's been exploring the surface of Mars for many years. And it's a sunset shot. It's actually about 80 minutes after sunset. So that's about where we are now in Britain. So this is the equivalent view. And you can see a horizon. And I hope you can see there is a dot of light, an evening star in the sky, just as if you go outside now, you will see Mars in the night sky. When I zoom in on that dot, you see it's actually a double star. This is the Earth and the Moon hanging in a Martian sky, a dose of cosmic perspective that we get by thinking about Mars and imagining being on Mars. So the fact that we can go there and take a picture of our home is mind-blowing, but it's symbolic of the fact that by exploring Mars and understanding its story, we get to learn more about our own planet's evolution. And by thinking about life on Mars, we get to understand much more about life on Earth. So those are the thoughts you should have in your head as we meet our experts for the evening. So at this point, let me try and stop screen sharing. Should be able to do that. And then let me introduce our first guest and expert. I'm delighted that we're joined by John Bridges from the University of Leicester. John is part of the team who run the Curiosity rover, which took that photo that I just showed you. So, and John, you're going to take us through a history of space exploration at Mars. Over to you.
Okay, thanks very much, Chris. So I'm going to just start sharing my screen and just have a few slides before we start talking. And okay, so to Mars to explore, that's the inscription we've got on our current Mars rover, the Curiosity rover. We've got it on our little sundial there. I think that encapsulates what we're trying to do with the Curiosity rover and indeed future missions. We've got a radically changing view of Mars, even for as long as I've been studying Mars, which isn't that long, sort of 20 years or so. But really, in some ways, perhaps we've come back full circle to some of the initial ideas or concepts that Herschel and the 19th century astronomers, amateur and professional, had about lakes on Mars, rivers on Mars. There was, if you like, a sort of lull during the latter part of the 20th century when these ideas really seemed a bit sort of out of place. But in some ways, although they may have been right for the wrong reasons, if you see what I mean. And here's just a little advert for one of our billion pixel images, a place called Glen Torridon. One of the fun things we do is to get to name the localities, and I've been naming localities out of thousands of places on Scotland. This one is Glen Torridon, and that, of course, is a bit of a selfie of the rover itself. But how did we get there? And why did we get there? Well, if we go back, take a sort of stopping off point at the beginning of the space age, 1957. If you were to look up the Wikipedia of the day, which was Encyclopedia Britannica then, this is what you would have seen about Mars. So here were pretty much the best views of Mars just at the dawn of the space age. Although we're seeing really a fantastic view of Mars at the moment, nonetheless, you have to say it is challenging to get details on Mars astronomically. So, where are these dark patches? Solis Lacus is a famous one with these vegetation, lichen, lakes. So if we've been having this meeting, say, in sort of around, I don't know, 1940, 1950, year of Sputnik, that's what we would have been discussing. What are the dark patches, the light dark patches on Mars? Is that some sort of seasonal variation where we go into lakes and vegetation. So that, of course, was one of the motivations for wanting to get to Mars. So fast forward to 1976 and into the early 80s with the 2 Viking orbiters and the 2 Viking landers. And there's a sort of a classic image, and we've all seen it, that mosaic of thousands of images stitched together from the Viking orbiters of the Western Hemisphere. And those pixels, the smallest of them are about 8 meters. Now, most for Viking are sort of tens to hundreds of meters. So it was in these images about this sort of era that there were these intriguing, important images of these, what people thought might be fluvial channels by analogy with what we see perhaps in, say, the Atacama Desert, somewhere like that. So although at face value it's just a very simple image, you know, but really encapsulated within that, there's an awful lot of information. If those really are from running water, then there must have been a hydrological cycle. There must have been some sort of groundwater. There must have been some sort of lake for the water to flow into, some sort of evaporation, clouds, etc. So a lot of implications in seemingly simple images for that, and that sort of kept open the idea of going back to Mars, even though, you know, the ideas of earlier on for current day lakes and vegetation seemed implausible. Nonetheless, it was clear that in ancient Mars, you know, maybe that might be a decent sort of description. But that raises one of the major questions. We know from sort of 1970s era that we have a very thin atmosphere on Mars, which isn't able to stabilize liquid water. So really the story of this change of Mars from what we call warm and wet to today's very cold and dry environment is one of atmospheric loss. Where did the atmosphere go? That's one of the sort of parallel questions that we have to address in our big picture of how did Mars get to its current cold and dry state when it once was so very different. So again, sort of 1976 view of Mars. Here's Viking 2, Utopia Planitia. Incidentally, that's where the Chinese lander Tianwen-1 recently launched is heading back to. Perhaps we'll get a slightly different view if it lands, I don't know, just over the hill or something. So here was our 1970s view of Mars. So sort of rocky plain, maybe from floods or impact ejecta from nearby craters. And these were thought probably to be sort of lumps of basalt. So sort of interesting in their own right, but, you know, not quite the sort of the lake beds, the rivers, etc. So was Mars just a lump of basalt, of lava flows, cut up by impacts and an occasional flood once every 100 million years? Was that what water on Mars was about? But of course, Mars has a large, diverse surface, and we were just getting a very small snapshot. Fast forward into 1990s view of Mars, and we're starting to get what you might describe as high resolution images of the surface. So here's one. These are coming from Mars Global Surveyor, and here the pixels were about 2 meters. So if you've got 2 meters per pixel and you're looking down on something, then, you know, you could tell, for instance, if we were in a lecture theatre anyway, you could probably tell that we were a group of people in some sort of lecture theatre. And you can clearly pick out features like this, which is an ancient delta in the ancient highlands in the southern hemisphere of Mars. This one is called Eberswalde. So again, in what is on face of quite a simple image, it captures a lot of information, a lot of implications. Because a deltaic pattern here, what's happening is the sediment is being disgorged down rivers from the ancient islands and must be flowing into a standing body of water, a lake. So there must be stable liquid water, and there must be a very active hydrological cycle. So, and also deltas, that's where you can trap organics and signs of life. So again, you know, we need to get there. So here's our 2012 to 2020 view of Mars with the Curiosity rover looking towards Mount Sharp. And here, within a month or so of landing, and we were successfully drilling for the first time on Mars, here at a place called Yellowknife Bay. So here, even at the early stages in Mars Science Laboratory, the scientists on the team, we were debating, are these layers lava flows or are they ancient lake beds? So as soon as we landed, we drove around, we went right up close, by which I mean, that close, that we realized, yes, we really have landed on a lake bed, we're drilling into it, and eventually, and after analysis with the SAM mass spectrometer and using X-ray diffraction, all the experiments we've got on our well-equipped Curiosity rover, we found clays formed by the action of water. We found organics trapped within the sediments. So yeah, this is warm, wet Mars, or it was rather, when it formed about 4 billion years ago, 3.8, 4 billion years ago. So that's one of my favorite images of Mars exploration, I think. It's just one of the sort of black and white, if you like, navigation camera mosaics, but it just shows robotic exploration of the solar system quietly ticking over. And we've been working for 8 years now, and no sign of it stopping, happily. Okay, so we were talking earlier, Mars is red. Well, okay, yes, Mars is red, but only sort of that amount of Mars is red. The top fraction of a millimeter is red. When you drill below it, you get into a very different Mars, which has been protected from the extreme harsh UV and other radiation on the surface of the planet. So when you drill into Mars, it's a rather grayish blue, or a whole range of tones. So we've been successfully drilling with Curiosity, now about 26 successful drill holes. And this is going to be followed further with ExoMars, with its 2-meter drill, and Curiosity and the Perseverance rover, i.e. Mars 2020. This is part of a large Mars sample return architecture, which will drill, cache for samples on the surface of Jezero crater to be brought back subsequently by a fetch rover and Mars Ascent rocket. So exciting times. Curiosity is leading the way. It's not just the sort of sedimentary hydrological cycle, though. In brief, remember I said in Viking era, we thought Mars was just sort of dark black, primitive basalt, a sort of iron, magnesium, silica-rich igneous rock, the sort of thing you see on Hawaii. But actually, we're seeing this a much richer variety of igneous rocks as well, and some of the float rocks scattered around through impact and brought down by rivers from the ancient highlands into gale. So we see these unusual silica aluminium-rich samples. This one called Ascoval that we're studying. So we're not just learning about water on Mars. We're learning about how the planet formed, how the crust differentiated from the mantle. So there's a rich variety of science that we're getting out of landing and roving on Mars. So here is my postcard to you from Mars. It's what we're going to be doing over the next 2 years on our mission. We're going to be driving up here through Mount Sharp. We're sort of in the foothills here now, what's called the Green, getting towards the Green pediment. And as we drive through and up Mount Sharp, which is about 5.5 kilometers high, I don't suppose we'll reach the top, but let's see how far we get. We'll see this transition from warm and wet Mars with those ancient clay beds, remember, at Yellowknife Bay, up to the colder, drier, more desiccated Mars, more sulfur-rich Mars, closer to the current environment. So we're going to go over that transition, try and find out what happened on Mars. Why did it change from that habitable planet to today's rather more inhabitable planet? Okay, so at that, I think I'll hand back to Chris. And
well, thanks, John. But let me ask you a couple of questions, because I think this stuff and to hear about your adventures with Curiosity is so fascinating. So I think let's start with that idea that there has been this change, which I mentioned, in which you're emphasizing, from this nice warm wet place you'd be happy to go on holiday to one that's more of a geologist's paradise. Can you give us some idea of what might have happened to make that transition? What are the ideas that the team are investigating?
Well, we must have lost a lot of atmosphere. So to stabilize lakes like in Gale Crater, you would need bars of pressure. In other words, sort of something like the atmospheric pressure of the Earth, or of that sort of order of magnitude or more, largely CO2. So where did it go? Well, Mars is a much smaller planet, so it's more difficult for it to hold on to its lighter molecules like hydrogen, oxygen. So there's also going to be a relatively high loss rate. So there is that. But there's another interesting factor. The carbon dioxide on Earth, it's sort of initial primordial budget that the planets came with, on Earth, that ended up in the White Cliffs of Dover, in limestone, in chalk, etc., nicely buried beneath the oceans. It wasn't quite so extreme a capture event, if you like, on Mars, but some of the carbon dioxide seems to have been trapped as carbonate. We've got a range of evidence for that from Martian meteorites, and the Mars 2020 landing site is going to somewhere where we think there was probably carbonate from remote spectroscopy. So some of that ancient thick atmosphere probably ended up in carbonate through dissolving in the water.
Yeah, it's that connection between the atmosphere and the rocks that I think makes this such an interesting scientific problem. So what's it like to do geology from a distance of a few million miles? When I look at this picture that you've got up on screen now, I want to go and walk into the hills, and I presume that your colleagues want to walk into the hills and hit it with a hammer, as geologists do. How different is that experience from working with the Curiosity team?
Well, really, we have to do everything more slowly. Okay, so if you're in the field on Earth, be walking up and down, goodness knows, I don't know, you might do 20 kilometers in a day or something like that. On Mars, we might drive maybe 100 meters in a day, something like that, and then take one drill hole, say once a month, and do a series of analysis, lots of laser shots. So we do things more slowly, basically, but actually that's quite good because it means we plan things out, we've got our strategy, we prioritize. So it's a sort of a slow, careful process, and we have to be careful we don't damage anything on the rover. Every day we have to make sure we're not pointing our telescopes, our cameras at the sun or anything silly like that, or we're not going to damage our robotic arm. We have to check that our rover isn't being damaged physically in different ways. So it's a more steady type of exploration, but in some ways that's good. So we do things very carefully, I think, is the answer to your question.
Yeah, and Curiosity, of course, you've got the instruments you took with you. You can't nip back to the lab for something else, which
yeah,
is part of the
but
problem.
You'd be surprised. We've been able to actually do sort of remote repairs, incredibly well. This is one of the things I found so fantastic, so exciting and impressive. We had problems with the drill, in that the percussive mechanism, the hammer mechanism on the drill, wasn't working properly. But we've been able, or JPL engineers have been able to do a workaround on that. So we're using the rotary action very effectively. Similarly, some focusing issues on the ChemCam laser. We now use imagery to focus. So actually, there's been a fair amount of successful problem solving as we've gone along, and likewise with software.
And the mission's lasted longer than was originally planned. And as you say, you're still climbing. Is there one thing that you'd like to find out while Curiosity is still exploring? Is there sort of one missing piece of the puzzle?
I think, well, we found that ancient Mars, the Gale Lake, was habitable. We found the chemical ingredients for that, the physical conditions. So we always wanted with Curiosity to get to this transition between warm, wet, and cold and dry. In other words, to get into what we call the sulfate unit, which marks that transition. So that's the major thing we've yet to do, and see what it looks like. What's the mineralogy? What were the fluids like? What was happening at this time of great environmental change? So I'm really looking forward to the next 2 years. This is a really important question in planetary science, and this is a unique opportunity to address it.
Well, we're looking forward to the results as well. If people have questions for John, then do put them in the Q&A if you're here with us in Zoom, and we'll get to them in a second. But I'm going to switch focus now. We always talk about Mars as a planet, but we're also interested in Mars because of its astrobiological potential, a place where we could look for life. And it's one of many such places that we're beginning to find and discover. So let me introduce our other expert, who probably these days needs no introduction at all. I'm delighted that we've got Jane Greaves from Cardiff University with us. Jane's team made headlines just a few months ago with a potentially very exciting discovery on Venus, of all places. But Jane's going to talk to us about the search for habitable worlds throughout the galaxy and the solar system. So Jane, over to you.
Thank you very much. And thanks to Lucinda for working the slides. I'm having quite a lot of internet trouble here, and you can probably hear Diwali fireworks in the background, which is nice, but I'm just promising you it's not a gun battle going on. But I hope you can hear me. Okay, let's indeed go to that slide. So I'm a professional astrobiologist, which is a real job, in case you were wondering. So I'm very interested by whether there can be life beyond the Earth. And our Earth in our solar system has unusual properties, and we know, of course, it hosts life because here we are. And so the Earth has a molten core, for example, and that helps do things like generate a magnetic field, which shields us from some nasty cosmic radiation. It also enables the surface to move about, so we have continents. So we're not just kind of like a ball with a uniform surface. We have continents and oceans and all sorts of things that contribute to life. And in fact, the other rocky planets of the solar system don't have that. They don't have these oceans on the surface, and indeed they don't have magnetic fields. And as John mentioned, they're rather different to conditions that promote life today. So a lot of the interest, I'm going to briefly talk about extrasolar planets, ones outside the solar system. A lot of interest is finding planets around other stars that are like the Earth, exo-Earths. So our imaginations say, well, maybe there's other life there crawling about, or even advanced life, something that might be giving us a wave somehow with signaling. So if we go to the next slide. This might be a surprise to you, but it would be probably familiar to people who remember this result from 1992. The first rocky planets found around another stellar object were not found around a star or anything like the sun. They were found around a dead star, a pulsar, which is a rotating neutron star. It's really nothing like a planetary system like our own. And this was a huge surprise, but kicked off a lot of the extrasolar planet research. So this is just an artist's impression. We don't have a detailed picture, but there are at least 3 little rocky planets there, and that's exciting. But this is really not a place where you'd expect anything to live. So instead of being steadily lit by a star, it's like living next to an X-ray machine in a hospital. Every few seconds, it'll sweep past the planet with a beam of X-rays and blast the heck out of you. And we don't think that's any way an organism could, harvest energy or anything. That just seems crazy. But if we move on a little bit in the story to the next slide, we do now know of rocky planets or about the Earth's mass around perfectly normal stars. So yellow stars like the sun or red dwarf stars, but normal stars that'll live for billions of years and steadily put out light. So if you're interested in the idea of habitability, I really encourage you to use this website. This is the Habitable Exoplanets Catalogue. It's maintained at the Planetary Habitability Laboratory, which is run out of a university in Puerto Rico. And it's a wonderful, usable website. And I just picked up this diagram from there today. So when people say potentially habitable planets, they usually mean a planet at about the right distance from its host star, that if there was an atmosphere about Earth-like pressure, that would enable it to hang on to liquid water on the surface. And that's the lack that unfortunately Mars has today. So we don't know about these planets' oceans and atmospheres, if any of them have them. But in terms of the heating by their host stars, they look okay on that grounds. So I had a quick look, since Mars is our topic for tonight. And in fact, there is one sub-Terran planet in the habitable zone of its host star, TRAPPIST-1. And if you look at the details for that, it's almost like an extrasolar Mars, our very first extrasolar Mars. So actually it's about 50% bigger across than Mars is, but it's definitely a lot less than an Earth. So that's quite exciting for thinking not just about exo-Earths, but other interesting planets. So if we move on one slide. Okay. So this has kind of got people thinking, and in particular, as Chris mentioned, we're really interested in signatures of life elsewhere. So from an extrasolar planet point of view, this is a bit of a problem because life may not exist at the same time as us. So we're looking at planets, maybe we study an extrasolar planet for a few years or decades, but that star system and planet system will exist for billions of years. We might just not be looking at the right time. You know, if we looked at an exo-Mars, we might be looking at it when it's completely desiccated, not when it had those wonderful oceans and clays and possibly even life earlier on. So we're kind of veering as scientists of the point of view of, you know, don't throw away any planets, don't discard them, keep them as possibilities for life. So in the diagram, we're looking at ones discovered by NASA's Kepler satellite. And in the red part of the diagram, they are mostly too close to their host star, where it says like about 1,000% of sunlight relative to that on Earth. That's going to be really baking them out. But you can see one, for example, that's a bit in the middle of the diagram, like where Venus is. So there is now work being done, not on just on exo-Earths and exo-Marses, but exo-Venuses, if that's the correct plural. Okay, so if we go on to the next slide. As Chris mentioned, the search for life in the solar system was originally thought to be you know, maybe quite easy. So I found this nice cover from the science fiction magazine, Amazing Stories. I think it says May 1926 in the top corner there. And at that point, everybody was writing stories about the complex life that would exist on Mars, how we would interact with those civilizations. So that's just about 100 years ago now. And unfortunately, our picture has changed and we're not going to meet this beautiful butterfly creature. Because, well, we certainly haven't so far as we've seen our robotic explorers go around on Mars, and we're not expecting to. And so, as all of us as speakers have said, we think conditions today are really challenging on both Mars and Venus. So Mars is very dried up, and Venus is also very dry, but it's very hot. So it's possible earlier in the history of the solar system that both Mars and Venus had liquid water on the surface. For example, the core of the planet would have supplied some heat to the surface, and that would have helped maintain nice conditions for liquid water. So if perhaps billions of years ago an ecosystem got started, completely independent maybe of the one on the Earth, that might possibly have got quite complex, but the conditions there today are so harsh that we don't think anything complex like this butterfly man could survive. But possibly there are niche habitats where very tough and small life, something like bacteria, could survive. And that's why I've got a little bit interested in Venus as well as Mars. So if we look at the next slide. Okay. This, to start with, seems crazy. This is one of the very few images we have from the surface of Venus, and that's a very heroic lander sent from Russia in the 1980s. It turned out conditions are so hot there that the lander could only survive physically for under an hour, and yet it was able to send back at, you know, byte per second kind of data rates, enough information to get pictures back. The surface of the planet is so hot it can literally melt metals. So that's presumably what happened to that poor lander. It's now some kind of puddle on the surface. Conditions there are also very high pressure. That'd be really bad. It's something like 90 times Earth's atmospheric pressure. So, okay, clearly no life. But if we move on to the next slide, there is a long-standing theory that the high atmosphere of Venus could be a last gasp habitat for some kind of bacteria originally on the surface of Venus that have floated up into the clouds. And the clouds of Venus, the high clouds, although they're quite acidic and quite dry, they're actually a bit like temperature and pressure at the surface of the Earth. So my team did this really small experiment. We used literally a few hours of telescope time to go, is there anything we can say about the clouds of Venus? And this is all remote observing. And to be honest, the spacecraft hasn't landed since the 1980s, but there are hopes for the next few years and certainly the decade after that of sending more advanced spacecraft. But until then, we can look with telescopes. And this is my personal favorite. This is the James Clerk Maxwell radio telescope in Hawaii, where I was lucky enough to work for a few years. That's on the sacred mountain of Mauna Kea there. We're very privileged to observe from there. And we were able to look at Venus and discover something very interesting. So if we go to the next slide. Okay, this is an artist's impression, and this always makes me laugh slightly. This was drawn for us to show that we're investigating the upper atmosphere of Venus, not the surface. What we actually wanted to look for was molecules floating in the atmosphere, because there are some molecules on Earth that indicate the presence of life. And one of these is phosphine. It's a molecule made of 1 phosphorus atom and 3 hydrogen atoms. And on Earth, it's a waste product for some kinds of bacteria. So I thought, well, we've got this crazy idea of these floating bacteria high in the clouds. Maybe they would put out phosphine, and that's one of the things we can actually detect with radio telescopes. So what this diagram is supposed to show is radio waves coming up from the sort of middle atmosphere of Venus and being absorbed by these molecules of phosphine. Although I've got to admit, it always looks to me like the molecules are teleporting out of the planet, like there's something in Star Trek, but I try not to tell the artists that. Anyway, next slide. Okay, so what we did then was turn the power of the Atacama Large Millimeter Array, many telescopes on Venus, and we found, again, what we'd found with the JCMT in Hawaii. If there's no molecules there, you get a flat line graph, which in these spectra, but if there are the molecules there, you get this V-shaped dip, which we now see on a couple of places of the planet with ALMA. I should say you're literally the first people to see this, because I produced this figure yesterday. So we're very excited about this idea. There might be phosphine, and it might have a biological source on Venus. So I think that's nearly me. If we go to my final slide. Yeah. So not just Mars, there could actually be these microbes floating in the clouds of Venus. It's a very speculative idea, and it's probably too challenging because of the acid and so on. But, you know, it's a possibility, and there are other possibilities we're going to send spacecraft to explore, like below the ice of the Jupiter's moon Europa or Saturn's moon Enceladus. There's a kind of seafloor potential habitat there that a spacecraft could peer into, and that's thought because that's liquid water and as sources of energy. Maybe there could be even some simple life or even larger life living there. So I think the solar system as a set of habitats is really exciting. But let's go back to Mars and hear a bit more about that.
Thanks, Jane. Wonderful overview of really cutting edge astrobiology, which is great. Now, questions are pouring in. If you've got questions, particularly for either of our speakers, do type them into the chat box wherever you're watching this, and we'll do our best. I'm really enjoying a question that's just come in from Becky, probably for you, John, but Jane, if you want to chip in as well. Becky wants to know, when people arrive on Mars, how known will the planet be compared to how much the astronauts who went to the moon knew about the moon or knew about where they were going? So let's say we land, let's say the 3 of us head to Mars and get there in 10 years' time. What will we know compared to the state of knowledge of the moon in the late 60s?
Yeah, that's a great question. I mean, in the Apollo era of 1960s, our view of the solar system was really changing. For instance, it was only really in the 60s that the idea of impact craters, which we now understand have really sculpted the surfaces of the inner solar system and the moon, that was firmly established. So the Apollo era, our views of the planets and the moon was really changing. But Apollo itself really moved forward and changed our view of how planets form and how they evolve into their structure. So I think there was, I think the answer to your question is we will probably know more about the Mars landscape that the Mars astronauts land on than the Apollo astronauts knew. The Apollo astronauts were worried about sinking into the dust, for instance. You know, we know that that's not going to happen on Mars. So I think actually, because we're exploring Mars with the rovers in a way that didn't really happen on no Mars. So that would be my answer.
Excellent, thanks. I'm going to move on. We've got so many questions coming in. So Jane, this one's for you from Hugo, who's 6. He wants to know, could there be marine life under the ice on Mars?
That's a really good question. Thank you, Hugo. We think possibly there could be. So there's probably water, as Chris mentioned, under the polar caps, but it might be very salty water. That's what the indications are so far. So it'd have to be something that could survive in a kind of saltwater puddle. So it would be really exciting if that was a crab or something. But we know on Earth there are simpler things, smaller things than crabs, that can survive in really salt water. So you wouldn't see it necessarily if you scooped up a glass full of ocean, but there might be little microbes and things floating around in there, something you'd see under a microscope.
So this brings me to the next question from Jason Gilchrist, and it's a question for both of you, but I'll start with you, Jane, if that's all right. Question is, could we plan to look for fossils in the rocks? We've talked about geological sampling, we've talked about remote sensing, but what is structural evidence of life, sort of astropaleontology, if you like?
Yeah, I think it depends on how much has happened on the planet, because on Earth it's hard to find the very earliest signs of life because there's been so much geological change. So on Venus it's thought that there were enormous volcanic episodes that probably wiped out previous rocky structures on the planet, maybe a few hundred millions of years ago. So it might have been a bit of a race in timing, and I think it will be hard to find any fossils today. But I think John should talk about that question for Mars.
Yeah, if you're there, John, then yeah, fossils on Mars.
Well, yeah, I mean, the classic joke is we want to find where the dinosaur bone is. We can live in hope. I think it's going to be quite a subtle discovery or series of discoveries, I think, on Mars. I think we'll have to find isotopic signatures, organic compounds, some sort of physical traces of sort of primitive algal or microbial life. And I think it'll need repeat analyses. So I mean, I can imagine we have Mars sample return. One laboratory says, we found life. Another laboratory says, I don't believe it. We need to analyze it as well. So I think it'll take time and a series of complementary analyses. I doubt it'll be one dinosaur bone or whatever.
Sure, though, wouldn't that be fun? A follow-up question from Stephen King asked about complex organics. Now, you mentioned organic compounds, Joe. Can you remind us what they are and tell us what the state of play is with organics on Mars?
Well, yes, the SAM instrument has been finding organic compounds, some relatively long chain carbon hydrogen compounds and benzene ring-like compounds, sometimes which have reacted with sulfur. So we're finding it's a long, painstaking business, because as soon as you find an organic compound, you have to be absolutely sure you haven't brought it from Earth, or it's some sort of reaction with your instrument or whatever. So the people who analyze organic compounds have my great admiration for their patience and their endurance, because everyone was always skeptical about it. But we're getting better at analyzing organics with SAM. We're learning how to use the instrument in different ways. So we're finding bona fide Martian organics. So it's all pointing more towards this habitable environment at the time of the Gale Lake.
But just because you found organic compounds now, it doesn't mean there's life there now. Though I think that's often where people jump to when they hear organics. But.
Yeah, you can form organic carbon hydrogen compounds in a variety of ways, including life, but not just life. So that's why we're probably going to need a variety of information like isotopes, chirality, left-handed, right-handedness of compounds, physical signs. So I think it'll take a while.
So Jen, this is right at the heart of astrobiology, and I'm always interested, how much do we have to assume about the life that we're looking for? Presumably, I don't know, if you have squirrels on Mars, they'll produce a different signature from if you have dinosaurs or bacteria or whatever. Or how much are we assuming about what life is really like?
I think we try not to make assumptions. So one of the fundamental properties of Earth life is its kind of chemistry out of equilibrium. So it makes things that you wouldn't spontaneously get chemically. So if you found that a process that it took energy investment to make it, that would be a really good sign of life, I think. And you wouldn't necessarily need to know anything then about whether the creature had, you know, a shell or bones or DNA even. You'd have to look at other things that could put in energy. So one of the things with Venus is whether the energy source might be volcanoes, and, you know, nothing to do with life. So that's something that, again, scientists are looking at really carefully.
Yeah, and on a similar note, we're getting a few questions. Catherine Grimes on YouTube and Paul Snell, who both ask about the possibility of, if we're doing sample return, if we're going to Mars as we plan to get rocks and bring them back, do we have to worry about bringing back Martian biology? Could that be dangerous to us? Jane, do you want to comment on that?
I don't think it could, because everything would be curated super carefully, and we've always done the same the other way. So, you know, made sure astronauts didn't take Earth bacteria to the moon, and the future Martian explorers will be really careful as well. I think John probably has a more informed answer on that than I do.
John?
Well, what we call planetary protection does go back to rules under a United Nations treaty in around the early 1960s. It is a major factor in planning Mars sample return. It really adds to the complexity. So Mars is what's called a Category 5 planet, because it's thought there may have been life in the past and may even be extant, current day life. So there is a theoretical risk, which means the samples have to be initially analysed in containment, and there has to be a break in the chain of contact between Mars and Earth. That said, rules can change. So as we have a deeper understanding of Mars, including with Martian meteorites and the radiation environment and what we see with the Curiosity rover and other rovers, perhaps those planetary protection rules will be amended, and they won't be quite so onerous. So everyone is being super careful, but I think probably we'll edge towards changing these rules, which will help with Mars sample return. So maybe over the next sort of half dozen years, we'll see some sort of changing of these ideas.
Great. Well, we're very much coming to the end of our time, but let's see if we can get a couple of rapid fire questions in. So Graham Morrison, John, this is for you. Wants to know, what would we learn from digging deeper into Mars than we already have?
Yeah, and that's exactly what ExoMars hopes to do, the drill on wheels. Maybe as
this is the upcoming European mission, right?
Launch 2022. Well, basically, the deeper you go, the less the input from the harsh radiation environment, cosmic rays, UV. So the better preserved are the organics and any traces of life. So that's why you want to try and get below the surface.
Excellent. Changing topics, Jane. Shirley would like to know, what would be the next planet that you would like to turn your radio telescopes to look for signatures of life?
I think it's going to be Venus for a while. There are some things we can do for extrasolar planets, but that's really, really difficult. So the James Webb Space Telescope, which I'm not at all an expert on, but that's the new infrared facility that NASA is sending up, hopefully in the next few months. I think that'll be able to look for biosignatures from extrasolar planets, perhaps for the first time.
Excellent. Well, we are more or less out of time for discussion. Do stay on. We've got some observing coming up, which our hosts will take over for. But before they do, I just want to say that I've really enjoyed this discussion. If there's one thing all of you should take from this, it's that whether you look at Mars, at Venus, or at the wider universe, we're discovering more all the time. And I hope you'll follow along with the further adventures of Curiosity, the further adventures of Jane and her radio telescopes, and the further adventures of all of us as we try and understand more about our planet and the rest of the universe. Thank you very much.
That was wonderful. Thank you all for your contributions this evening and getting us started off so fantastically for our first virtual National Astronomy event. Absolutely wonderful introduction to Mars and the burning question about life in the universe. Thank you, professors. And we are not over yet. I have heard that we may not have clear skies in the UK, maybe some area around the UK. But however, I have heard that we may have a telescope in Cyprus that can show us Mars tonight. Robin, tell us what is in store for our remote observations this evening.
Hi, well, thank you very much to Chris and Jane and John. That was a really fascinating talk, but we're hoping to talk about actually seeing Mars in the night sky ourselves at the moment. as I said earlier on, it's one of the things that National Astronomy was famous for. And what we originally planned was that people would be able to go out and look at Mars in the night sky. And you can do this when it's clear. It's really obvious. And if you don't know where to look on the National Astronomy Week website, and it will give you explanations of how to do it. But we have some amateur astronomers here who will try and show you what you might be able to see if you had a large telescope of your own in your back garden. And I'd like to introduce now, if we can show our video to David Arditi, who is a colleague of mine in the West of London Astronomical Society. We have Ian Sharp, who's down on the south coast of England. We have at the other end of the country, Eric Walker, who's right up in Scotland. And so we were really spreading our options to try and get you clear skies. And we will be doing this every night of the week from 7 o'clock until 8. And hopefully we'll get clear skies in the UK. But those of you who are in the UK will know that the skies have been really bad today, just cloud and rain and terrible. But we have a secret weapon, and that is Agapios Elia in Cyprus. And he was telling me a short while ago that he has clear skies. And look, he's grinning there. So if you'd like to unmute yourself, Agapios, and I'd like to hand over to David Arditi, who will conduct the show from now on.
Thank you very much, Robin. So as Robin said, in the past, the major idea of National Astronomy Week is for people to get together with and meet their local astronomical society and go out into a dank, dark field, and for families to be able to view through small telescopes what is in the night sky. Obviously, with the social distancing due to COVID, we're unable to do that. So we came up with the idea of doing a virtual National Astronomy Week where we show you what is visible through amateur telescopes anyway, using the wonders of Zoom and video cameras, which can be attached to telescopes to transmit the images. So I'm in my observatory in outer London, and it is pouring with rain here, and there's fireworks going off everywhere. And every time a firework goes off, it rains even more. So it's terrible conditions. And obviously I've got the observatory roof closed, but I will be able to show you many images that I have been taking from outer London of Mars and other planets, if we have time. But since Agapios in Cyprus has got clear weather, I think we should go over to him as soon as possible and see what he can see and what he can tell us about what he can see.
All right, hello everybody. Greetings from Cyprus. We have clear skies at the moment. We also have fireworks. There's a small storm just behind me in my south, so you may see some flashes. But I'm gonna go ahead and share my screen and show you what I've been getting. We have Mars here on the screen, which you can see right there. Now, I'm using a reflector telescope. This is a 235 millimeter Schmidt-Cassegrain telescope, onto which I have attached a color camera. Now, for those who don't know, these cameras that we typically use to take images are not like your typical home camera or DSLR. They are sort of very similar to webcams, where you attach them to your computer via USB. And these can give very, very high speeds. We're talking about hundreds of frames per second. And we need this to be able to isolate the best moments in the atmosphere when the atmosphere is steady, and capture many images and later on process them and bring out all the fine details. And in fact, just before I took a small sequence of images and I processed it, and I'm gonna pull it up on the screen now and show you side by side to the live view what a stacked, as we call it, processed image of Mars would look like. So let me just zoom this in a little bit. And as you can see, On one side, we will have the live view of Mars, which is right there. And on the left side, we have the processed view of Mars. And you can clearly see the south polar cap, or what's left of it. And we are now, we have Olympus Mons is somewhere over
You can only
here.
see the live view, Agapios. I can't see the other one at the moment.
Okay, let me see if I can work this out. Okay, let's try that again. I will now pull up the image on the screen.
Not that
How
one.
is that? Not that one.
That's more like it, yeah.
Yes, so this is the processed view, and I'm going to put them side by side to show you.
I think, oh, there we go. Well done.
There we go. So there we are. So we have on the right, we have the live view, let's say, coming in from the telescope at this moment. And on the left, we have the processed view that I just took. And you can immediately see how on the left, it's a very sharp image. We have quite a lot of details. I don't know if David or somebody else would like to point out some of the details that we can see.
David?
We can see, this is an image with north at the top. So astronomical images are often shown with south at the top because astronomical telescopes invert. But this is a north at the top image, and we can see the North Polar Hood, which is this area of bluish white clouds at the top of the planet. And we don't see an ice cap on the North Pole, but we do see an ice cap on the South Pole, but it is very small, it's very shrunken at the moment because this is the southern Martian summer. The dark areas of Mars are the dark albedo regions. They don't bear any particular relationship to the height of the terrain, but we can sometimes in these amateur images see the volcanoes of Mars. We can't see any of those at the moment. We can see some of the dark areas. The area in the middle of the images is known as Margarifer Sinus. And we're seeing also parts of the Mare Erythraeum. These have names which are drawn from classical mythology. They were given to areas of Mars by Schiaparelli, the Italian astronomer in the late 19th century. And so they're similar to the names that we use for the moon, with names such as Mare, which means seas. But of course, they do not contain water, and they have nothing to do with the history of water on Mars that we've just been hearing about from Chris at Lintott and others. But we do sometimes also see in amateur images clouds on Mars, particularly what we call the orographic clouds, which are where the winds force moist air over the mountains, and then you get clouds over the mountains. And these are indeed clouds of water droplets. The atmosphere on Mars, to remind you, is only 1% of that of the Earth, so very, very thin. Nevertheless, there are winds on Mars, and they can be quite fierce, and there are dust storms on Mars, and we sometimes see those from the Earth, and they can be localized or they can be global. And 2 years ago, when we last had a close approach of Mars, it was more or less completely obscured by a dust storm, but we haven't got any dust storms visible at the moment. And Mars comes close to us every 2 years. So what we call the apparition of Mars comes every 2 years, because Mars takes approximately twice as long to go around the sun as the Earth does. So it comes into the same position with respect to the Earth and the sun roughly every 2 years. So what's your equipment like? You're not in an observatory, Agapios. you're actually set up outside. How do you do that setting up? How difficult is it to set up your equipment? What's your location like?
So I am just south of Nicosia, more or less in the center of the island here in Cyprus. And I have all of my equipment is kept outside in a typical garden shed. The telescope is set up on a rolling mount, a dolly type mount. So that allows me to quickly take everything outside, set it up, and line it up to whatever object I want to observe. And it's especially handy later on at night because I don't have to disassemble everything and pack everything away at the end of the night. I can quickly just roll it back into the shed. And this allows me to, spend most of my free time observing. So the equipment is a typical Schmidt-Cassegrain telescope, 235 millimeter on an equatorial mount. I don't know how well you can see it. And it can produce reasonably good images. And I'd just like to say that today we have at our disposal equipment that can produce marvelous images, whether somebody's just visually observing through the eyepiece of a telescope or taking images. We have access to such high quality equipment that almost anybody can acquire. Maybe not something like this, but something that will give reasonably good images and be able to observe not only the planets or the moon, but so many other celestial objects. In my case, I'm lucky because I don't have a lot of light pollution where I am. So I can do most kinds of observing with not much effort. And again, here in Cyprus, the weather is almost always favorable. Although we did have a bit of a scare tonight. There is a storm just south of me. But for the moment, everything looks good. It's nice and clear. So hopefully I can continue giving nice images.
Somebody has just asked on the Q&A, is this really the live view of Mars? And yes, it is, isn't it?
Yes, it is. Actually, it is. On the right side of the screen, this is the view coming from my telescope. I can tap it slightly and you can see it wobbling there. So yes, it is.
But why is it jiggling about? That's something that people might not understand.
So there's two things happening on the screen on the live feed. One is I am constantly adjusting to keep Mars centered because the telescope is not precisely set up tonight. I was in a hurry trying to get it out to avoid the storm. But the shimmering that you can see on the screen, that is actually from the atmosphere. Our atmosphere is constantly shimmering and churning. It is a fluid after all. So that is what you can see there on the screen, that's shimmering.
And that's what we call astronomically the seeing. People often think that seeing means how clear it is, but it's not actually the case, is it? It's how turbulent the atmosphere is. And you've got, what would you say, David? How is that a typical view that you might get from Edgeware?
Yes, I would say he's got reasonably good seeing. I would say about 5 out of 10. There's various factors in astronomical observation. There's the transparency of the sky, but there's also the steadiness of the atmosphere. The atmosphere contains many layers of different temperatures which can mix up. And the different temperatures and different pressures of air in the atmosphere give us different refractive indices. And those different refractive indices can cause the planet to appear to boil or to split up or to go in and out of focus or to move or to distort in various difficult to predict ways. And so this is the great advance that we've made in recent years. When we were dependent on film photography, it was never really possible to capture the planets properly because this constant movement would always blur out any photograph on film. The pictures that we saw in a presentation earlier, which were the best ever taken on chemical film, and they were taken, I believe, from the Andean mountains back in the 1920s. I think those were done by a famous expedition from the Lowell Observatory. But those are about the best that were possible. But now we can get far, far better results with far smaller telescopes through the technique that Agapios is using of a CCD camera or a CMOS camera, an electronic detector, capturing the images very rapidly. And when the images have been captured very rapidly and then they are stored, and then we can run software on them, and the software superposes the images. So what Agapios would take with his camera and his capture software that you can see on the screen there, he would capture a video file of Mars, and then he would combine the images, he would stack them into an image which contains all the images that went into the video. And the software can select out some of the best images. It can select out the sharpest images, some of the least distorted images, and it can actually correct for the distortions to some extent. And then when that's done, you get a final image, which still looks quite blurred. We may show this at some stage. You get a final image that looks quite blurred, but it contains a lot more information than is apparent. And you can use other software which sharpens the image up. Does what's called wavelet sharpening or unsharp masking. And then you get an image such as Agapios is showing us on the left-hand part of the screen, which contains far more detail than any of the individual frames contain. Any of the individual frames do not contain that amount of detail, but combining in this way is a method of increasing the signal to noise ratio. So, but indeed, you get best results when you get the best seeing. And from the UK at this time of year, we tend to have a high altitude, fast wind, which is known as the jet stream above us. And this can cause us a lot of problems, but it looks like Agapios is probably south of where the jet stream is going at the moment. You can get forecasts of the jet stream from meteorological organizations, and you can try and plan your observations for better seeing, but better seeing, like weather in general, is not really a predictable thing.
Agapios, do you think it would be possible to actually show us the process of how you improve that image you've got there by doing a sequence, taking a sequence of just maybe a
absolutely
few hundred images or whatever? And
we can do one right now. Okay, so what I'm going to do now is I'm going to reduce the frame size. Obviously, we don't need all of this black space. We just want to concentrate on our target, which is here. And I am gonna choose, let me just center it a little bit better over here. And I'm just gonna do a quick capture of 1 minute. And you may notice that now the image is turned into monochrome. And the reason for this is I want to be able to capture as many frames as possible. And I'm going to now, I've started the capture. I'm going to do 1 minute, and I'm currently imaging at about 112, 113 frames per second. So what's happening now is the camera is capturing 110 pictures of Mars for every second that goes by. So at the end of my 1 minute long capture, I'm going to have a very large number of frames out of which I can pick the best ones and combine them and then process them to bring out the details. We've just passed the halfway point of the capture. We are at 40 seconds. We have another 20 to go. And we've captured so far a total of 5,000 frames. So as you can see, there's quite a lot of data coming in. So we're just going to end now. There's our 1 minute coming up. There we are. So what I'm going to do now is I'm going to switch to my processing software, which is over here. Now, as David mentioned before, what this is going to do is going to take those frames, line them up, and analyze them so that we can get an idea of how how stable the atmosphere was or how turbulent it was. The software is doing that now, and it's come up with an estimation of where the best images are, and it's sorted those images to the beginning of the file. So I'm going to choose only the best frames. Now I'm going to go with 25%, and I'm going to stack those frames now. Now we're only stacking 25% of the total of the 5,000 frames that we got. And the software is now going to combine all of those images. There it is. And I'm going to go to another software now. And I'm going to sharpen the resulting image that came out of the previous software. So I'm going to open it up now. Here's our image. Now at this point, there's no processing done to this other than just stacking. So the image seen here is the result of the combination of the 25% of the file that we got. And I'm just going to process this now. I'm using what's called wavelets, a sharpening tool. And let me just try that again. And immediately you can see as I'm adjusting this, that the image is getting sharper and sharper, and there's a lot of details that you can see. There we go. I'm going to save that. And I'm going to pull that up on the screen. And that would be this image. So there we are.
That's really brilliant, isn't it? Yeah.
Oh, yes, I'll just mention we can actually see Olympus. Oh, it's gonna get. We can actually see Olympus Mons there, just about. It is a brighter patch towards the upper right. Yes, that's the one. That I believe, comparing that with my simulated map, which I've got here, which is actually the other way up, so I have to make an adjustment for that. So that's that white patch actually represents the biggest mountain, biggest volcano in the solar system, 20 miles high. So that is quite mind-blowing. I think that we can see a volcano with an amateur telescope on another planet, and in fact you can see that visually sometimes. It's often quite a bright point. Classically it was known as Nix Olympia, the snows of Olympus, because before, in the days of telescopic observation, before we sent space probes there, before we knew it was a mountain, we just saw it as a bright point of light. And you can, the dark bands across the middle of that image, that's called the Maris Cimmerium and the Maris Serenum. We've also got a bright area in the northern hemisphere, which is known as Cerberus, after the dog of the underworld. They all have these quite sinister names, the names that Schiaparelli gave to the features on Mars. They're all things to do with the underworld or things to do with death. I don't know quite why he did that, but Mars has always had a quite sinister reputation throughout history. I suppose it comes from the classical allusion of the planet of war. Anything else you'd like to tell us about what you're getting up to astronomically, Agapios? What else do you like to look at?
So my main interest is the planets. I spend most of my free time observing the planets of the solar system: Jupiter, Saturn, Mars, Venus. I also enjoy visual observing, especially lately. I've had quite a few chances to go up to the mountains here in Cyprus, Troodos, where we have reasonably dark skies, and it's a short drive from where I live, and I also some deep sky astrophotography, of course, is very rewarding as well. To be able to attach a typical camera onto a telescope and acquire images of very distant, very faint deep space objects, nebulae, galaxies. But I would say 9 out of 10 times I'm outside, I'm observing the planets. I just find them so dynamic. There's so many things going on the planets, as is the case with Mars. A couple of observers are reporting that there is a new dust storm. Unfortunately, it's on the other side of the planet than we can see now. Jupiter is such a dynamic world. There's so many features that one can observe, not only the Great Red Spot or the moons, and Saturn, and mostly, as I said, my main focus would be the planets.
One question we had online was, is it possible to see the moons of Mars live? And I just mentioned that now very quickly. Well, no, it is, but they are very much fainter than the main disk. So to observe the moons of Mars, you really have to increase the exposure, in which case Mars will be frightfully overexposed. So you won't see the two moons of Mars. They're very tiny and very much more difficult to see.
Yes, what Agapios was saying about the fascination of viewing the planets, I very much agree with that. I've followed the planets for 40 years, and viewing the planets is one way in which amateur astronomers can actually contribute to science. The results that we produce, even using quite small Earth-based telescopes, are actually of great interest to space scientists and to those planning space missions, because we can get an overall view of the planet that you can't get once you've sent a space probe and actually are in orbit around the planet or even landed on it. This is not so much the case with Mars now, because Mars is extremely thoroughly studied. There are quite a few probes in orbit around Mars at the moment, as well as landers on its surface. But with the outer planets, certainly with Jupiter and Saturn, amateur observation is absolutely vital. There is currently the Cassini, the Juno mission. Cassini was Saturn. There's now the Juno mission to Jupiter, and that is in orbit around Jupiter. It's studying the magnetosphere and it's taking pictures of the cloud tops, but they can't get the overall view of Jupiter that we can get from amateur Earth-based telescopes. And because we've got a network of amateur astronomers all around the globe, we can cover every time zone, because somewhere in the world there will always be an amateur astronomer, most likely, observing the planet. And so we are unlikely to miss any new events. And if something new and exciting happens on Jupiter or Saturn, we're likely to spot it, and we're likely then to be able to alert the professionals, and they will be able to put bigger telescopes, the Hubble Space Telescope, or if there are probes in orbit around the planet, as there is with Juno and Jupiter at the moment, they'll be able to study these features more closely. So we do have actually a good cooperation and a very fruitful collaboration between amateur and professional astronomers in planetary science. And indeed, as an amateur astronomer, I've often been to professional meetings and meetings of space scientists and talk to them, and they've been always very delighted to hear what amateur astronomers can offer to add to their research. Because another thing is that we've got a very long record. We've got databases of what we've seen on the planets going back at least a century. So we can tie in the detailed observations we can get from space probes now with a longer term historical record. The British Astronomical Association, which I'm a member of and I'm kind of representing tonight, we have records of Jupiter and Mars and what was seen on those planets going back more than 100 years. So we are positioned to be able to spot long-term cycles and long-term changes in the atmospheres of those planets. So thank you very much, Agapios. That's actually fantastic. You got us off to a fantastic start with the live observation of Mars. So I'm very glad that we decided to have you because it
You're
seems to be
very welcome.
It seems to be, and we may have time to go back to you later on, but Mars won't change very much. So that's a last look at Agapios in Cyprus and his setup, his telescope mounting and so forth, and all illuminated by the red light, which is quite important for astronomy because it doesn't damage dark adaptation so much. So that's why we tend to use red lights in astronomy, in case you're wondering about that. So what I thought I'd do, since it's pouring with rain here, I thought I'd show you my telescope. And I've got a video that I made of my observatory on a sunny day in the spring. So I'll see if I can show you that. I will see if I can share my screen and also share my computer. Oh, I can, yeah, share computer sound. I can share the media player. Let's see if I can do it like that. And then I can play this video. Now this is going to last 10 minutes and 40 seconds. And then after that, we will go over to Ian Sharp in Sussex to see what he's up to, and also check in with Ian Walker in the Scottish Highlands to find out what conditions are like there. So this is me giving a little tour of my observatory, which is quite an ambitious observatory by amateur standards, but this will give you an idea of what kind of thing we get up to. Hello, this is David Arditi, Director of the Equipment and Techniques section in the British Astronomical Association, and in this video I thought I'd give you a little tour around my observatory equipment located in my garden in the northwest London suburbs. So, welcome to my observatory. Let's go in. The observatory is of the runoff roof shed design. It's a rectangular construction, wood and plywood and corrugated plastic shed, which I designed to be an observatory, although not around the specific telescopes that are now in it. I designed it in a modular fashion so I could easily modify it. It's all bolted together, bolted and screwed together rather than nailed together, and in fact I have extended it a couple of times as I've installed larger telescopes in it. So the roof is made of corrugated plastic on a wooden frame, and once it is unbolted it simply pushes back. Here are the telescopes. The main telescope is Celestron 14, which is here. This is actually just the dew shield of the telescope. The body of the telescope is up here. Small telescope underneath here. This is a Lunt 60mm hydrogen alpha telescope. Up here I have a 100mm ED refractor. That's a 900mm focal length refractor, and there's a camera mounted here as well. All this is mounted on this very large astrophysics servo drive, astrophysics 1200 go-to mounting. German equatorial mounting. Here are all the counterweights. This is the go-to controller. Once that's switched on and powered up, it's a sunny day today so it's hardly possible to see the display. The display has a list of objects such as Messier objects and solar system objects. So if I choose with a keypad the number 4 code is for solar system objects, and then I can choose number 4 again, which in the list of solar system objects, that's Venus, and then here's the rest of the keypad. Then I press go to, and it starts moving, and it remembers the time and its latitude and longitude and where it was last pointed to in the sky and where it was synchronized to. So it will now be pointing at Venus, which is very high up, as you can see. It's very close to transiting. Let's see how accurate that go-to was. Looking through the finder telescope. Yes, Venus is indeed there, just to the left of the crosshair and below the crosshair. Here's the sun as viewed through the hydrogen alpha solar telescope. The camera might not pick up much. There are a few small prominences visible and the usual granulation in the solar photosphere. You'll see that the subsidiary telescopes are mounted in adjustable tube rings so that they can be accurately pointed in the same direction as the main telescope. So the mount will always drive all the telescopes to look at a given object that you program in. So you have to be careful, therefore. If you tell it to go to the sun, all the telescopes will be pointing at the sun. So you really must be careful to make sure that they're all capped up, apart from obviously the solar telescope. The hand controller, as I demonstrate here, allows the telescope to be driven around by hand as well. That's a fast rate of movement. You can that's actually 600 times sidereal rate, and you can tell it to slew at different speeds. So at 64 times sidereal rate, that's a much slower rate of movement. The telescopes are mounted on several aluminium blocks, and those are on concrete, and this main cylindrical concrete pier down here, this was actually cast in some stainless steel bins, and this column goes about 3 feet below the ground. The floor here is wooden boards, and these are slightly isolated from the telescope pier. On the top of the boards I've got carpet tiles which can be easily removed, and they make a nice soft landing when equipment is dropped, such as eyepieces and cameras, which obviously can be sometimes. An awful lot of wires here, as you see, an awful lot of wires connected to the telescope. Most of them run down the pier, and some of them go under the floor and reappear on a shelf over here, on a big shelf which has places where the PC can be connected. But some of the wires actually go out of the observatory, go up the walls, disappear out, and go across to another shed, which is the warm room shed, which I will show you now. Here is the warm room, Tom Summer House behind me, and you can see it's only a few meters from the observatory over here, and it's connected with lots of wires which run slightly overhead and into the warm room. And here you can see a PC which is connected to the camera on the Celestron 14, and you may be able to see there a very blurry image of Venus on the screen. So this is the image from a USB camera sent over the 5 meters or so to this warm room, and I can control the telescope from here. I'll show you by pressing buttons on the screen with the mouse. We can gradually move the image of Venus around on the screen. There it goes. And we can focus it as well. By pressing this manual focus button, this sends a DC signal to a motorized focuser on the telescope, and the image of Venus is now coming into focus. This is in full daylight. This is about 4 in the afternoon now. And that's a focused image in infrared light at 990 nanometers. People often ask me about systems for remote controlling telescopes, and it is quite complicated. It takes a lot of work to set up, even a short range remote control of a few meters. The main characteristics are that you need to be able to remotely slew the telescope, and you need to be able to remotely focus it. I can't remotely uncover the telescope or remotely operate the observatory roof. Those have to be done by hand, but it is very close. You can see the telescope just out there, so if something goes wrong, and things do go wrong sometimes slews don't work, telescopes move unpredictably in the wrong direction through some programming error, then I can see what's going on and hopefully head off any disaster. And there again is the live focused image of Venus on the screen. Another thing I can do here is use an iPad displaying a planetarium program to show exactly where in the sky the telescope is pointed. This is very useful, and this can be operated at the same time as the astrophysics pointing software, because there are actually 2 serial connections to the astrophysics mount. Here Sky Safari showing on this iPad is showing that we are indeed pointing the telescope at Venus, and it shows us that it's near the Pleiades, but we cannot see the Pleiades now because it is full daylight. And it would also be possible to control the telescope using these arrows on the Sky Safari interface. That was the video about my observatory, and I think we'll go over to Ian Sharp if we can, and see what he's up to. He's in Sussex, somewhere near Chichester, and he's going to... one question we've had, Ian, is about refractors and reflectors. So maybe you could talk a bit about types of telescope and their characteristics. We can now see the observatory.
Okay, so I have a domed observatory in my meadow outside of our garden here in near Selsey, and this is a telescope probably very typically like the one you were seeing images of Mars. This is an 11-inch Celestron Schmidt-Cassegrain telescope. I'll talk about the different sorts of telescopes as I go. A quick introduction then. This is my observatory. I built this and designed this myself. I built all the, it's 3.2 meters across. This is in just the other side of the garden here. Here's another artistic shot of it. Wooden base and a big concrete pillar. I chose a dome because here it's very windy, and if I was to have a sliding roof like David's, I think I would still suffer too much from the wind shaking the telescope too much. I do observe outdoors as well when it's not too windy. Here's another shot of my observatory with the moon and Venus. And just to say, I love doing all sorts of astrophotography and observing. I love taking images of the planets and Mars, other solar system objects like comet Neowise, which we had recently. This is an image I took just back in July. I do a lot of photometry as well. I'm studying a number of stars with another team of amateurs. We're looking at various binary stars, measuring their transit times as they revolve around each other. We can detect exoplanets that way. So that's another very big interest of mine. Another comet I took in Spain. I travel for my astronomy. This was taken in Spain in 2014. Comet Lovejoy with its tail stretching back to the Pleiades. Deep Sky Worker, this was with a remote telescope. I do like using remote telescopes. You can actually rent time on telescopes. This was taken in a telescope that I rented time on in Australia. It's a lovely nebula in Centaurus. Here's an image of Jupiter I took back in 2011 in Barbados. I do travel with my telescope to we mentioned about the seeing conditions, and if you go to certain locations, you can improve the seeing conditions in places like Barbados, which is quite famous for very good planetary seeing conditions. Other images that I've taken, I shall move rapidly on. Galaxies, nebulae, I do all sorts of images, and here's Mars that I took, an image I took back just a few days ago at the end of September, and it's been a great apparition of Mars. Some Saturn images showing the different tilt of the rings. These are all taken with the telescope you first saw in the dome there. Okay, so what I thought I might do, if it's okay, I might do something slightly risky. And now if I go back to, I don't want to share my screen anymore. I want to go back to the video. So I now need to see. So can you see me on the, or is it, I'm looking at you again, David?
We're only seeing you and
okay.
your room.
Right. So what I thought I might do is I'm moving my webcam around, and what I thought I'd do quickly is show you some of the bits of kit that you would have hanging on the end of the telescope to take an image of a planet, a bit like we were seeing from Cyprus just recently. Now, this is I've got this in next to me in the office because it's raining outside. I've taken it off the mount. This is my 11-inch Celestron, so it's 11 inches. We tend to use old money in telescope terms, so it's about 280 millimeters across. So this telescope has got a mirror here, and the light comes in from the end here. I think you can just see here we go, the front of the telescope. The light goes in here, goes down to a mirror. It comes back out to a focus somewhere beyond the end of the telescope, but another mirror here reflects it back down through this tube and this focuser here. This is the focuser, where we get the focused image. And so what that means is, with a telescope like this, with this Schmidt-Cassegrain type of telescope, is the telescope folds the focus. So it can be shorter and not so long. If this was a straightforward Newtonian, it would be at least twice the length, and hence it would be very unwieldy. And also, if it was a refracting telescope, there would be a lens at this end and no mirror. And so the lens would bring the focus directly to a focal point here where we would focus. But again, the telescope would have to be very long if it was a refractor, and it would be extremely expensive. Typically refractors like this one here on my shelf behind me, there's a refracting telescope where it has a lens here, much smaller. Otherwise, they're very much more expensive to make as large as this telescope. But briefly, then I'll show you what we use to take images of planets. If we want to look at the planet, we can use an eyepiece such as this. And what that would go in, that would just, this whole arrangement, which I will explain, will come out, and the eyepiece would plug in, and I would, we would look in there. And to make it more convenient, you can use things like right angle prisms because you can rick your neck trying to look into the telescope, so you can bring the focus at 90 degrees to make it easier to observe. But what we're looking at here is a combination of equipment. I've got you see how this plugs into the telescope. I hope is this clear, by the way? Is this okay?
Very clear.
Good. So what I've got in here is to take an image of the planets, you tend to want a very high magnification because the planets are tiny in angular size. So you need to magnify them very greatly. Now, this telescope is quite good at giving a large image. It's got a long focal length, f10. But we want more. So this is a Barlow lens, and this would typically multiply that by a factor of 2 or more. So we would end up being above f20, focal length of f20, more magnification. And then at the end here, this is one of those specialized webcam type video cameras that we were seeing. Now, this one is not a color camera, it's a black and white camera. And this arrangement here is a filter wheel, and it's got things like this. Here's a filter. This is a visual filter, but it's got 5 of those in a wheel that's driven by a motor, and it can rotate them one at a time. So there's a filter in line with the light. So what we do to take a picture of a planet using a mono camera, where we can get higher resolution, is we take a video with red filter, then one with green, and then one with blue. And we process those individually in the similar way as you saw Agapios doing from Cyprus with the same process. And then we blend those images together to produce the color, the final color image. So this is the typical equipment that you would see. As you see, I can unplug it and replace that with an eyepiece if I want to do some visual observing and tighten it up like this. This is the focuser. You can see it moving in and out, and a fine focus. And we typically use electronic focusers as well, so that we don't have to touch the telescope. We can focus at a touch of a button, and we don't joggle around as much. So anyway, that I think, sorry, I've probably overdone my time, I'm not sure, but that was what I wanted to show you, was some of the equipment at the back end of a telescope. David, is there anything else you want me to say, or?
That's all very interesting, but I'm feeling a bit grateful, a bit guilty rather, that we haven't spoken to Eric in the Highlands yet. So I'd like to do that. We're getting quite a few questions in. Some of them we may not have time to answer. There's like one about the disadvantages of it. Are there any disadvantages of a Schmidt-Cassegrain scope? Would you say there are any disadvantages, Ian?
It certainly is a great all-round telescope, but it's not the greatest telescope for wide-angle, let's say, faint galaxies and wide field viewing. It's not great for that, but it's a very fine all-round telescope, especially for visual observing.
Yes, I would agree with that. You do get a bit of light loss due to the multiple optical elements, but it's not really severe, and the general portability and usability probably outweighs those. So thank you very much. We'll be hearing again from you a couple of times this week, I expect, Ian.
Thank you very much.
Everybody, do, if you're really interested, if you've enjoyed it, do tune in same time tomorrow. And you never know, we might have good weather in somewhere in the UK, and we'll get some slightly different views of Mars. So now I'd like to ask Ian in the Highlands if he'd like to tell us what's going on there weather-wise, and what he can tell us about what he does there astronomically.
Well, good evening, David. You're calling me by my brother's name, Ian. My name's Eric.
Oh, sorry, I'm always
not a problem. Not a problem. I'm just going to share my screen and hopefully kick. I've got a tiny little, well, a presentation about what Highlands Astronomical Society is all about. Something has gone a bit awry with the Zoom webcast, but I'm sure it'll come back. Just bear with us. There appears to be somebody jackhammering in the background.
Oh, that might be the Diwali fireworks around my observatory.
Oh, course, that's what that will
So
be.
that's I'll mute that.
That's okay. It's okay. I've got a little not responding sign up here, which is a bit of an irritation, considering it's ran rather well up until now.
Well, that's always the way, isn't it?
Yeah.
Is it still pouring with rain there as well?
It's absolutely, it is terrible. It's not pouring with rain. We had some rain. It is now just that lovely thick cloud. You mentioned the jet stream, David. And of course, up here in this part of Scotland, we tend to be right into it at this time of year. And it just brings so many lows over. Oh, I think something happened there. I think you still see me okay, guys?
We're seeing your camera, yes.
Right. But you're not seeing my share screen, are you?
No.
No. I think I'm going to have to abandon, I'm afraid, David.
Well, we can try again later in the week.
We can. Well, I'm on Friday, and hopefully the weather forecast is actually for the onset of early winter. And if I can get a cold, frosty, stable night, that will just suit me fine.
Yes. Well, good to check in with you, Eric. We got the name right this time.
You did. That's fine.
And we'll see you again soon. I'm just looking at the questions. Got a question from Sabur. Mars was formed by the same dust and materials as the Earth. Why is Mars so different from the Earth? That's a good question, isn't it? It's the magnetic field is a very big factor in the Earth. The Earth's magnetic field protects us from the solar wind, and that has prevented our atmosphere from getting stripped away. And it's the stripping away of the atmosphere of Mars by the solar wind over billions of years that has really led to it being this very desiccated and low atmospheric pressure place. So it's all due to, I think, the deep history of the solar system, where the materials ended up. And in general, in the solar system, the heavy materials went to the center, as you'd expect. Well, they went to the planets nearest the sun. So Mercury, Venus, the Earth has a lot of very heavy materials and a lot of iron in the Earth's core, a lot of iron and nickel. And so that resulted in this dynamo in the Earth's core, giving the high magnetic field, which didn't happen so much with Mars. Mars has a lot less of these heavy metals in it. And then the outer planets are gas, and the planets beyond that are in the ice belt, and Uranus and Neptune are made of ice. So the time is now exactly 8. So probably our time is up now.
We can, if we can go through to Agapios for one last look at Mars, if it's still there. Agapios, could you unmute and tell us what the situation is? There he is.
Yes, it's still pretty clear. I'm running a sequence now on Mars. Let me just share my screen again. There we are. I hope you can see it.
Yes, this is just the black and white version.
Can you see Mars on the screen?
Yes.
Yeah. I'm running a capture now. It's still clear, and I'm about to complete a small sequence of captures and do some processing. Let me just go ahead and do that now and see what's changed. Probably.
Tell us one thing.
Okay.
What is the temperature where you are at the moment?
At the moment, it's about 12 degrees Celsius outside.
Oh, there we were thinking
for Cypriot standards,
roasting.
Yes, well, for Cypriot standards, 12 degrees Celsius is a bit cold. We're used to very high temperatures. So this is why you see me all bundled up. We're not used to cold temperatures in Cyprus.
That really is a lovely image. That is really quite stable image.
Someone wants to know what is the Bortle rating for the sky. That is the transparency of your sky at the moment in Cyprus. What's the best it gets, in fact?
For my home location here, it's bordering on about Bortle 4. If you want to talk by sky quality measurements, here at home you can get about 20.4. But the darkest here in Cyprus, up in the mountains, would probably be north of 21.8, 21.9, which is considerably darker than here at home. And the good thing is it's a relatively short drive away. Cyprus is a small island. You can travel from one end to the other in 4 hours or so, 3 hours.
Well, that's a good plug for the Cyprus Tourist Board. Well done. Super image. Thank you very much to Agapios for showing us Mars, which we had given up all hope of seeing from the UK, but tomorrow is another day, and hopefully we've got another week of observations to show you, and it would be great to be able to bring some from the UK as well. I'll just start my video now. Thank you to everybody. Thank you to David, Agapios, Ian, and to Eric for coming on tonight. Remember, as I say, we'll be here every night this week from the show starts at 6 with talks about astronomy, about Mars in particular, and then from 7 onwards we'll be looking at the sky. Maybe in the next few days we'll be bringing you pictures of Jupiter and Saturn, which are also up in the sky at the moment. I think they will have set for from Cyprus at the moment, but hopefully we will see them, if not live, then in shortly recent recordings. So with that, thank you to everybody. Thank you to Lucinda for bringing the us live and being the director of the show. She's been working away hard in the background and sending us little messages like a director should through our, if not through our ears, then through the chat. Okay, and back to Lucinda, and she will now close the show. Thank you very much indeed.
Thank you, everyone. Just if you guys want to turn your cameras and say goodbye, wave, and just it was just a phenomenal evening for there's way more people involved in getting this started. We're going to have an incredible 8 more days of this, so we hope you join us. And then we also have daytime events Monday through Friday, 11 to 12 from science centers around the UK. I hope you will join us, and we hope schools will also be a part of it. We are live streaming on YouTube, so there's lots of opportunities. Registrations don't close until 2 hours before we start, so there's still lots of opportunities to join us here on Zoom. But from NAW, from the National Astronomy Week, have a good evening.
Bye.
Bye.